Are there doubts from the previous session?
Excuse me, sir.
Yeah, go ahead.
Before you take that a small operational query, can you check the link I posted on the chat box, the meeting chat box, the link to a discourse post? Could you verify
I've
that if
seen that
possible?
Discord post.
Okay, yeah, I
Just a
tagged you
moment.
in that as well. Actually, the thing is, nobody has clarified anything yet.
Okay,
So
okay,
neither
okay.
Lavanya
I
ma'am
was
nor.
actually, yeah, I was not aware of this bonus activity showing up. Just give me a moment.
Okay, okay. I can describe the actual issue. So
Okay, just a
the
moment.
yeah, I'll wait.
Okay, yeah, go tell me what's the issue?
Yeah, so the confusion arises because Lavanya ma'am in one of the initial sessions, she had mentioned that no additional bonus activities would be set up for marks. At
Yes.
least that was what she said. But
Okay.
now, so now there are a couple of questions which have been put like there. It states bonus on the portal. So,
Yes, but it also
so
says not graded.
not graded, correct. So not
Yeah.
graded refers to it is not part of the graded assignment. But the moment you put the word bonus in there, the confusion naturally arises, right? And on
Okay.
top of that, someone has also responded to the thread saying it will fetch bonus marks, and I believe that person is a student.
Okay,
So yeah,
okay.
I
I
just wanted
think
to
he
the
is
official
a student.
clarification.
Uh,
And the
as
TAs
far
are
as
not.
I know, there's no bonus activity this term. We were planning to introduce it initially, but then we couldn't get it up and running in time. So probably for the next one, we will
Okay,
have something like that. I think this is a bonus activity, yes, as in you can do it for your own.
right. Similar to practice and activity, like similar to every other
Yes,
that is
yes, yes,
non-graded,
yes.
right?
Yes, yes. As far as I know, that is that. I'll talk to Lavanya and I'll just clarify it on that discourse post itself.
Right. So one thing at least, can you ensure that if, like let's say it is a bonus activity that will fetch bonus marks. Can you
Yeah,
announce that officially if that is
yeah,
the case,
yeah,
and
yeah,
at least give us maybe
yeah.
1 week to solve it if
Yeah,
that is
sure,
indeed the
sure, sure.
case.
Okay, okay, okay. I don't
Yeah,
think that
that's
is
that's
there's any bonus points in this terms uh,
right.
thing.
Sure, sir.
So
That's up.
yeah, I'll make an official announcement. I'll probably have a mail sent out to everyone as well regarding the confusion and
If it is not if it does not fetch bonus marks, just clarifying on the thread itself should be sufficient. But if it does
okay.
fetch bonus marks, maybe an email announcement should be sent in that regard.
Sure, 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 sure.
All
Okay.
right. Yeah. Thanks, sir. That's all. That's all
Yeah.
I had.
Yeah. There was another raised hand, I think.
Yeah, I believe Neha also raised her hand. Neha
It
Kumari.
was just no, I just raised it accidentally, so sorry for
Okay.
that.
Yeah, no problem, no problem. All right, then let's get started. So I believe inner products were introduced in the last session, and you know what length and angles are in a vector space. That is part of week seven's thing, right? So you know everything about. I mean, you know the notion of lengths and angles and inner products, general inner products on and norms on a vector space. Is that right? Okay, we'll continue from there. So the topic for today's session will be orthogonality, and then you have relation with linear dependence, orthonormality, and then if there's time at the end, we'll take up. But there should be time. These are not. to involve topics. So let's take up projections as well. So okay. Where we are in the big picture, a quick recap is we know what a vector space is. You have a set to operations. You know what it means to add two vectors. You know what it means to scalar multiply a vector with a scalar. And of course, real number into real number, what you know what that means. And now there is a notion of inner product, which is some sort of a product between two vectors, which gives out a real number. So this is vector plus vector giving a vector. This is scalar times a vector, which is another vector. And inner product is a bilinear form in the sense that this is the input is two vectors and the output is a scalar. So what does this scalar signify is, roughly speaking, how much along one vector is the other vector. So if I have something like this, how far is it from being along? So that is what the inner product signifies. Of course, this is made more clear when we talk about the notion of angle that is induced due to this thing. Angle between two vectors, if the angle between vectors v and w is theta, then cos of theta, you know, is this quantity. Right? Now, if v and w were along each other, what do you mean? What do I mean by v and w are along each other? V is some scalar times w. So they're on the same line, right? So when they're on the same line, one is just a scale of the other. This is how it is interpreted. So what happens to the cos of theta? Cos theta would just be alpha w w divided by norm of alpha w, which gets a mod alpha. So this becomes plus or minus 1 as and when the sine of alpha is plus or minus 1. So the angle is either 0 degree or it is 180 degree. So this is why inner product gives you a sense of how much along one thing is. And if there is no uh, dependence, or projection is a word that will come up later. So if I have something to be orthogonal in the usual sense of how we understand it, then we know that, so this thing is plus or minus 1. If v and w are orthogonal to each other, are perpendicular, let me call it perpendicular, because that is the more common nomenclature, perpendicular to each other, then in terms of the angle, you would interpret that as theta is equal to 90 degrees, right? This is what you would understand it as, or cos theta is equal to 0. But as soon as you say cos theta is equal to 0, you will have that vw divided by norm v norm w. This is 0. So in at least the usual dot product, this would be v dot w is 0. Or more generally, in an inner product, you would want to call vectors which have inner product equal to 0 as orthogonal. And that's what we'll be doing. So definition. Vectors v and w. In a vector space, all of that data is given. are said to be orthogonal or perpendicular. Note that in a general vector space, let me call it orthogonal and write perpendicular as the alternative nomenclature. Now, in a general vector space, it is not obvious to see. You have this diagram, right? Here, this thing we can do in, say, R2 or R3. In general, in Rn, maybe we can still see it. But more general vector spaces, abstract vector spaces, this may not be as immediately visible. So you have to formulate it in terms of the inner product. And the formulation is this. Or equivalently, angle is 90 degree. Angle between V and W, that is understood. So to check whether or not two vectors are orthogonal to each other, what do you have to do? You have to compute their inner product, whatever inner product is given. Maybe the standard inner product, the standard dot product that you have on Rn, if you have Rn or a subspace of Rn, and it is given that the inner product that you're considering is the usual inner product, then you have to just compute the dot product and see if uh, it is equal to 0. If it is equal to 0, then they're orthogonal. If it is not equal to 0, then they're not orthogonal. So this is an if and only if thing. Why are orthogonal vectors important? That will come a bit later, probably in this session itself. So, but this is how to check for orthogonality.
Sir,
Yes.
can you just move up that plus or minus 1? Yeah, sir, in this case, theta is equal to 0, right? When
Theta
V
is
and
equal to
W
0
coincide.
or
Yeah.
180 degree. So if it is minus 1, then it is pi, that is 180 degree. So if you have two vectors, V and W, which are in opposite directions, then the angle between them is 180.
Yeah. Then what is the relation between V and W when theta is equal to 180?
Yeah, V will be some
Like,
alpha times W, which alpha is negative. So if you do this, so the alpha comes out, right? So this is alpha WW divided by modulus of alpha W
yeah.
square, the norm of W square. So this gets cancelled with this. So what
Okay.
you're left with is alpha by modulus of alpha,
It's
which is the
1.
sine of alpha, which is 1 or minus 1, depending on alpha is positive or negative. Alpha is not 0. We don't, I mean, the dot product of 0 with any vector is 0 itself. So we are taking non-zero vectors and comparing. I mean, when we are talking about angle, that is what we need to do. And this is plus or minus 1. And this is from the image also, it is clear, right? If alpha is positive, then it is some positive scalar. So let's see over here. If I have vector v, and I say a positive scalar multiple of this, that would be something along this direction itself and in this side itself. But if I have something to be a negative scalar multiple of this vector, I would assume that it is along the same line, yes, but in the opposite direction. Of course, all of
Yeah.
this in visualizable spaces like R2, R3, or Rn.
Yeah. So what I understood is if the angle is 180 degrees, then one vector is the uh, negative scalar of the another.
Yes, that is how we interpret wherever angles make like conventional sense. In the sense that, okay, what do I mean by that? So if you have some other uh, inner product, like I cannot think of an example maybe on the spot. You could have vectors like this in Rn. So this is very much dependent on the inner product is what I'm saying. You could have some vector in Rn where these, okay, these vectors will always be orthogonal to each other, irrespective of what uh, inner product you take. But things like this and this, these might be orthogonal to each other also, depending on the inner product. So you have to compute the inner product over here rather than just say the dot product. Suppose you have inner product of, let's say, x1, y1, x2, y2 is equal to x1, x2 plus y1, y2 minus x1, y2 plus x2, y1, something like this. This also can be checked to be, or is this? Do I need something else? x1, y2, x2, y1, xy, xy. This should be fine. Yeah, I think this is an inner product. So this is the standard inner product, but I'm also saying it is minus something else. But that will still be positive, definite, and all those conditions for the inner product you can verify. Now, if I take 1, 1, 1, 0, we have 1, 0. Yeah. Consider, for example, 1, 1, 1, 0. This will be what? 1 plus 0 minus x1, y2 plus x2, y1, which is 1. So this is 0, right? But you know that in your conventional inner product, you would not call this angle as 90 degrees. But this is why the notion of angle is dependent on the uh, inner product that you choose. So you can have a non-standard inner product giving the non-intuitive notion of angle. The angle, that is why angle is something that is motivated by what we find in the usual Rn with the usual dot product. But after that, it just becomes this guy, the cos inverse of this. That is just the angle. That is what you call the angle. So when you make interpretations like that means they lie along each other or they are orthogonal to each other, they don't cast a shadow and all that, you have to be careful that this is with respect to some chosen inner product. And this might not behave visually or geometrically in the same way that you would expect it to, even if it is in art, for example. Just a caution note, that's all. But the understanding is correct that if I have theta to be 0 or 180 degree, then it has to be, if it is 180 degree, for example, then it has to be a negative scalar multiple of that. So for example, 1, 1 and 1, 0 are orthogonal in R2 with, let me call this guy some, I'll call it just 2, but don't pay too much attention to the 2. It's just to differentiate it from the usual one, I'm just calling it 2. So if I define the inner product on R2 as this quantity, then you can check that, okay, sorry. Then you can check that 1, 1 and 1, 0 are orthogonal vectors. But in the usual one, it is always better to start out with the usual one because that is what we understand easily. X0 and 0y for arbitrary x and y, these are orthogonal to each other. In, I'll call it standard R2. Standard R2 means R2 with the usual dot product. All right. Why is this? What is x0 inner product with 0y? This will be x times 0 plus 0 times y. It's x1, x2 plus y1. Right? So this will always be 0. Right? And in the standard version of the R2, of course, this is obvious also. if I take any vector along which lies along the x-axis, positive or negative side, and let's just draw the thing over here. If I have any vector in the y-axis, those things are orthogonal to each other. Yeah, is there a doubt?
No, sir.
No, sir.
Okay, so why are orthogonal vectors special? So that's what we will see. And before that, another definition. So this was for two vectors, right? If I have two vectors, then orthogonality between them is defined by the vanishing of the inner product between them. Now, if I have finitely many vectors, let me call it v1, v2, vn. Said to be orthogonal. If the inner product between vi and vj is always equal to 0 for all I not equal to j. So pairwise, you need orthogonality between, it's like given any pair of vectors, any pair of distinct vectors vi and vj, you need their inner product to be 0. Of course, I should not be equal to j, because if I have vi, uh, that will be norm of vi square, which can never be 0 unless vi itself is 0. So, but for unequal, as in distinct set of vectors, vi and vj, if you have uh, the inner product to be 0, then such a set is called an orthogonal set. So to look at an orthogonal set, for example, let's see R3 with a standard inner product, with a dot product. Can you give me an example of orthogonal set?
One zero zero one.
Let's say I want three. I want three vectors.
010
Make in the standard basis.
Yeah, the standard basis.
001.
Okay,
001.
something other than 001.
004.
Okay, something other than
000.
00, something other than 00y
Yeah, this
or
will be
000, whatever. Is it possible?
No, it shouldn't be.
Yeah, it feels like it should not be possible. Let me write down 001 and then we take up that question. The fact that 001 is a candidate is clear, right? Each pair is the dot product will be 0. Visually also you know this, even if you compute it 1 times 0 plus 0 times 1 plus 0 times 0, you can compute the dot product of this with this with this, and this with this, and verify that each pair has, they're like mutually orthogonal vectors. Each pair has inner product 0. So this does not give me, there's no problem here. This is an orthogonal set. Right, but yeah, coming back to the question of, can there be some other third vector? So side question, it's like, what are all possible? I'll just call it extensions of 100 010 to an orthogonal set with 3 vectors. Like I want to add one more vector so that it remains orthogonal. How will I complete it? So suppose XYZ is a candidate. XYZ is orthogonal to 100, implies this has to be 0. But what does that imply?
X is equal to 0.
Yes. And similarly, if I see that this has to be 0, the dot product of XYZ, this is how I would extend it to a mutually, to an orthogonal set, right? It has to be orthogonal to the existing vectors, all of the existing vectors. So this will also force Y is equal to 0. So together, this forces this to be of the form 00Z. And yeah, Z is equal to 0 is also okay because it is convention to take 0 vector to be orthogonal to everything, but typically we avoid that and say Z is not 0. But what about extensions of, so does every orthogonal set of R3 have to look like X00, Y00, 00Z? What about extending, let's say, just I start out with one vector. Is how do I add two more vectors so as to make it an orthogonal set? Is this the only way? This and multiples of this? Or
No,
are there
there
other
is. There
possibilities?
are ways. There are other ways.
Yeah, any example?
I think is I can imagine just keeping 100 and flipping the other two. I mean, just shifting the other two by a nudge.
Yeah, give you an explicit example if you can.
Okay, let's go with 020.
But as soon as I do a 020, then your third vector will be something of the form 00 something, right? I don't
Okay, no,
want
no, no.
multiples of these vectors.
Wait, not 020. 1 second. 100.
So I
Okay,
can
how
do
about
this. Okay, yeah,
yeah,
go
yeah,
ahead.
yeah. Yeah, I was going there. 011,
Okay.
and then the Z guy has to shift to
So
1.
this works actually. Does this work?
Yes, sir.
Yeah,
It may work.
it does work. It is not, it may. This is an orthogonal set that can be checked quickly,
Oh,
right?
sir,
It's
in
like
last also we can take if 111.
you cannot take the last one to be 111. You, if 100 is there, then 111 will not be there because 100 and 111 are not orthogonal to each other, right?
Yeah, I got it, sir.
Yeah.
Sir, 111 is a linear combination of first two vectors. No?
Yes. No, no, if as long as 100 is there, 111 cannot be. Even if you don't use these vectors or something like that, 111 can never be there when I start out with 100. So orthogonal sets, checking if a set is orthogonal is quite straightforward. Look at what your inner product is. Take each distinct pair, compute the inner product, and if all of those guys are 0, then it's an orthogonal set. If even one pair of vectors are not orthogonal, then they are not an orthogonal set. Now, why do we look at orthogonal sets and why are they important? One of the most important things in linear algebra, as we have seen time and again, is that linear independence, right? Linear independence gives me a way to manufacture basis. So every vector space has a basis, but checking whether a given set of vectors is a basis typically involves uh, some Gaussian elimination, writing. So how do you check something is a basis, right? Checking if a given set is a basis, or linearly independent even. If this thing is linearly independent, involves setting up an equation of this form, involves solving for C and Vn equal to 0. So after you set up this equation, how do you conclude whether it is linearly independent or not? Can someone quickly recall?
So if only it has like a trivial solution, then I think it is
Then it is
linearly.
linearly independent.
Yeah.
If it has some non-trivial solution, it means that some of the vectors are dependent on some of the other vectors. So that is linearly dependent. And typically, this is a procedure which involves some Gaussian elimination, even in things like Rn, or you represent it in some coordinates and then use some Gaussian elimination. Right. So how orthogonality helps us is if you have the notion of an inner product, then you can have. So this is a one-way implication. Orthogonality implies linear independency. So if I know that a given set is orthogonal, then it is linearly independent. The converse is not true, obviously. Take, for example, this is something like a caution 1110. This is in the standard one now, not the other alternative definition. So let's not get confused with that. Let me give something else. 3410 is linearly independent, that is clear. But not orthogonal. So it's only one way. Orthogonality implies linear independence. We'll see a quick proof of that. So suppose V1 to Vn is an orthogonal set. Now I want to say that this is linearly independent. This is my starting point, that it's an orthogonal set. My end point is this is a linearly independent set. So to prove that, what will I consider? I'll consider the equation C1V1, the sum of Ci this is equal to 0. If I can somehow prove that this equation has only the trivial solution, then I'm done. So in order to do that, what will I do is take the inner product.
Sir, I have a question.
Yeah.
If a set is orthogonal, then it
Yeah.
necessarily means that it is linearly independent. But the inverse is not true, right?
The converse is not true. Yeah.
I mean, it's converse. It's not true.
Is not true. Yes. Yeah. That is this caution. So the converse is not true. Take the inner product of summation Civi with Vg. So if I write inner product of summation Civi with Vj. So this j is some fixed number between 1 and n. So what does this become? This is inner product of 0 with Vj because I have this thing. So this is nothing but 0. Inner product of the 0 vector with anything is 0. So I have this fact to be true. Now you can use the linearity properties of the inner product to conclude that. So if I have a plus b, or let's use vector notation only. If I have v1 plus v2 with w, I can write it as v1w plus v2w. Right, so this becomes summation. So this is for two terms, what I've written on the side, but this carries over for finitely many terms anyway. So for each of the terms from 1 to n, you will have this thing. Right? This is linearity. And I can further apply linearity, or I can bring the scalar outside. This is also something that my inner product allows me to. And I get this equation. Summation Ci times inner product of Vi Vj is 0. But what is inner product of Vi with Vj? Because I've assumed this to be an orthogonal set, right? What does that mean?
Sir, it should be zeros if I is not equal to j.
Yeah. So if I is not equal to j is fixed and I varies from 1 to n. J is again fixed. It's a fixed number between 1 and n. So as I vary j, there will be only one term which is possibly non-zero, which is actually non-zero, and all the others are 0, right? So I'll just get Cj norm of Vj square is equal to 0. Is this step clear?
Yes.
Okay.
Yes.
But you know that norm of Vj square is never 0 unless Vj itself is 0. So here maybe there's some conventions where orthogonality plus no zero vectors. This is just making sure that no funny business happens. So you could have this some set like this. This is, and if v1 and v2 are orthogonal to each other, then this may be called an orthogonal set. I don't know the exact convention what is being followed, but most of the time you have zero vector is orthogonal to every vector. So I want my set to have no zero vectors, because if you have even one zero vector, then linear independence fails. You know that, right? So here the non-zeroness of norm of Vj square forces Cj to be 0. But this j was fixed. It was a fixed number from 1 to n, but it was arbitrarily chosen, right? I can do the same thing with v1, v2, v3, and I can conclude that Cj is equal to 0 for all j. Correct? But what does that mean? That means that this equation has only a trivial solution. In other words, this is linearly independent. So this is why orthogonality, this is one of the applications of orthogonality, that if you know that a given set is orthogonal, then it has to be linearly independent. This is also somewhat in agreement with the earlier notion that the inner product captures in some sense how much along uh, one vector the other vector is. So if I have two vectors and they're orthogonal to each other, then they can never be along each other unless one of them is 0. Uh, but we are taking non-zero. So orthogonality implying linear independence is not surprising considering that intuitive starting point that we have. This proof also tells you how to determine coefficients. Now, if I have, suppose, let's say expressing a vector as a linear combination. Let's call it this.
Sir, if you
Combination
scroll up
of
the last line that you wrote, did you mean to write independent?
yes, yes. Thanks. Yeah. This has to be independent. So now if we look at the problem of expressing a vector as a linear combination of a given basis, or linearly independent set is also fine. So take, for example, let's say express three, 4 as a linear combination of 1, 1 and 1 minus 1. So what are the coefficients? So I know that 3, 4 is equal to, I know that 1, 1, 1 minus 1 is a basis. First of all, this is a basis. Is that clear? You can appeal to the special case of R2 and say that they do not lie along the same line, so they have to be linearly independent, and the dimension of R2 is 2, so this is a basis. Or you can just look at the inner product of them, the standard dot product of them, and then you see that that is 0, so they are linearly independent. That way also you can conclude that this is a linearly independent set and hence a basis using any of the methods that you know. But then how will I write this as this? So I have to set up this
So x is
equation.
equal to 7 by 2.
We have to set up this equation, and then what is the solution that you get? X is equal to
7 by 2.
7 by 2.
And y is equal to
Minus 1 by
7
2.
by 2 minus 4. So minus 1 by 2, I think.
It has to be mentioned. Yeah. So this was a simple example, but let's look at it at using the method that we used in the proof itself. Like if you have an orthogonal set, you know that while you multiply it using any of the orthogonal elements, everything else vanishes, right? So if I do start out with 3, 4 is equal to x times 1, 1 plus y times 1 minus 1. So I take the inner product of each side with 1, 1. So I get 1, 1 dot 1, 1 plus y times 1 minus 1 dot 1, 1, which is 0. Well, let me write it. This part is 0. And this is 7. And this is 2. And so x is 7 by 2. Similarly, if I take the inner product with 1 minus 1, I get the first term to be 0 and the second term to be again 2. And this will give me y is equal to minus 1 by 2. So determining the coefficients also can be done using orthogonality. If you have an orthogonal basis, then finding the coefficients is easy. In this case, solving this system of equations was also not very hard. But in general, computing the inner product, you will have to compute one inner product on this side and one inner product on this side. And that gives you the coefficient with respect to an orthogonal basis. We can do better. That we'll be getting into the next section. But I hope it is clear that orthogonality can determine linear independence. And when there is linear independence, it can also be used to compute the coefficients of any vector in the span of the given linear independent set. Is that clear? Is that much clear?
Yes, sir.
Yeah. So orthogonality is a property that we have used. We have used only one aspect of the two things that we were saying that are made possible because of the notion of an inner product, that is lengths and angles, right? So angles we used, and we took the extreme, one of the extremes, that the angle between them or the inner product is 0 implies what angle is it? It is angle is 90 degree, and when the angle is 90 degree, what happens? So this is what we have seen. Now the other thing is lengths. This is the definition of an orthonormal set. So here, I'll just write it this way. An orthogonal set in which every vector is of unit length is an orthonormal set. So there are two things to check. So if you are given a set V1 up to Vn, to check for orthonormality, you need to do two things. One is Vi Vj is equal to 0 for all I not equal to j, and Vi this is equal to 1 for all. So each of the vectors in the set are unit length and they are mutually orthogonal to each other. Take any pair, they have to be orthogonal to each other. This is an orthonormal set. So this is even more special than an orthogonal set. This is an orthonormal set. And what happens in the case of orthonormal set? Once again, as for examples, the standard examples, the standard basis is an orthogonal set. It's an orthonormal set also with respect to the standard inner product, of course. But this basis, this is orthogonal, but this is not orthonormal. Why?
Because the length of the first vector is not 1.
Yeah, length of either of the vectors is not 1. So is there a way to go from orthogonal to orthonormal?
Yeah, there should always be a way, right?
Yeah, that's what I'm asking.
Well, we just chop it off or add something to it.
Yeah, what can you make it more precise? So
Maybe
what?
scale it in some way that it becomes one.
Yes, that's closer. Now tell me, what do I need to do to this set to make it orthonormal?
Swap the
I think we have to divide each vector with its norm.
So here, what do I do? So what do I do to this set? Just give me the answer.
Mm, 1 by square root of 2 times 1 comma 1. Yeah. Um, yeah. 1 by root 2 comma minus 1 by root 2.
Yeah. So this works. The idea is correct that you have to scale it in some way, and the scale is exactly the norm of the vector. So if V1 is any non-zero vector, then V1 by norm V1, norm V1 is not 0 because I'm considering non-zero vectors, is a unit vector. Unit vector means a vector of unit length. Why is this? If you look at the norm of, or let's say inner product of V1 by norm V1 with V1 by norm V1. This is what? So I can bring out the norm V1 out because of linearity. That becomes norm V1 square. What I'm left with inside is just V1 V1. But this is again norm V1 square. So these two cancel with each other and this gives me 1. But this is nothing but norm of V1 by norm V1 square. And this implies that norm of V1 by norm V1 is 1. Right. So if I'm given non-zero vectors, then by scaling, I can make them unit vectors. And it is geometrically also clear, and it can be verified that if I have V and W to be orthogonal to each other, then any scale of V will be orthogonal to any scale of W. Why is that? Because if this is, yeah, this is one fact. If V and W are orthogonal to each other, again, non-zero vectors, I'll probably not, okay, let me write that also. Non-zero vectors, then non-zero scalar multiples of V and W are also orthogonal. This is also not hard to see. Why? Because if I take CV and C1V and C2W, again, because of the linearity property of the inner product, I just get this to be VW, and that is 0. Again, you need to be comfortable with both notions of the geometric interpretation, and if you have to prove it just using symbols with abstract vectors, both of them you need to be comfortable. Here, all I've used is linearity property of the inner product. So why did I do all of this? To say that it is possible to go from orthogonal to orthonormal. So the idea that if I'm given an orthogonal set, you have to scale it was the right idea. But of course, you should be careful there because that was probably made without taking care of the fact that scaling does not influence orthogonality. But now we have taken care of that. If I can, so the first statement is that given a non-zero vector, I can scale it to make it a unit vector. And the second statement here says that scaling by non-zero factors does not influence orthogonality. So using both of those two statements, this is a particular example. You know that this can be generalized now, that if V1 to Vn is an orthogonal set, then what is an orthonormal set? What are the elements?
V1 by norm V1, comma V2 by norm V1, and so on.
V2 by
Vn
norm
by
V2.
V norm V2 and so on. Vn by norm Vn.
Yeah. So going from orthogonal to orthonormal is possible. Now, why do I need this sharpening? Why am I not happy with orthogonal? It's because expressing coefficients is even sharper now. Expressing vectors as linear combinations. once again, okay, here I'll probably take the general expression. If I have, suppose V is a linear combination of, assume that this is a basis of a basis V1 up to Vn. So I know that V can be uniquely written as C1 V1 Cn V. But what are these coefficients? To determine these coefficients, typically you have to, again, just as you as we did over here, we have to set up a system of equations and solve them, Gaussian elimination, whatnot, right? But suppose I know that this is orthonormal. What changes if I have the fact that this is orthonormal? Look at V inner product with V1, for example. This one will be C1 V1 Cn Vn inner product with V1, which by linearity is C1 times V1 with V1 plus C2 times V2 with V1, and so on up until Cn times Vn with V1. Right now, I know that this is orthonormal. So what are all these terms? All of these guys over here.
So C1.
This is 0, and this guy is 1. So this is C1. So C1 is
And
inner product of,
no, no, okay, sorry.
okay. V with V1 is just C1. In general, using an inner product with Vi, you can see that Ci is just inner product of V with Vi, correct? So to determine coefficients, now it is very simple. You just take the inner product of the given vector. Suppose I want to express V as a linear combination of an orthonormal basis given by V1 to Vn. Then all I have to do is compute inner product of V with V1, inner product of V with V2, and inner product of V with all of the given vectors, and I'll get exactly the coefficient. Right. So any vector V can be written as inner product of V with V1, V1, plus inner product of V with V2, V2, so on up to inner product of V with Vn, Vn. So this is the specialty of an orthonormal basis. Are there any doubts as to how we got here? How we got to this expression? Yeah. So this is, so if I have an orthonormal set, in particular it is orthogonal, and if it is orthogonal, then it is linearly independent, and if it is maximal linearly independent, then it's a basis. So if you have a maximal orthonormal set, that is a basis. That follows just from that. So if I have an orthonormal basis, then expressing every vector is simple using the inner product, given the inner product. So the pursuit is to find orthonormal basis. Now, for vector spaces which are Rn, it is easy, as in it is just the existence of orthonormal basis or explicit examples of orthonormal basis, you can just take the standard basis. Now take, for example, let's take in R3, the space given by x plus 3y minus z is equal to 0, for example. So I know a basis for this. Can anyone tell me a basis for this space? Do a quick computation and come up with a basis for this. Okay, how would we go about constructing a basis for this? Any ideas?
Yes, sir, computing.
Okay.
One zero one 013
101
013.
013. Yeah, this works. I'll probably get the same thing. It'll be x, y, x plus 3y. So that's 101 and 013. Yeah. So this gives me 101 and 013. But can you come up with an orthogonal basis for this? Now, if this is still a simpler example. But if you are given a point and you want to express that point as a linear combination of 101 and 013, you cannot use the previous trick of just taking inner product because this is not an orthogonal basis, right? The inner product of this with this 101, 013, this is equal to 3.
Yes, sir.
So can you just look at it and come up with a orthogonal basis?
Just a minute.
Or is it possible that there is no orthogonal basis?
Is it possible to just comment by just looking at the vector? It's like
Yeah, that's what I'm asking. Is it always like, can you just look at it and say that this is an orthogonal set? Yeah, give me an orthogonal basis. Can you do that? Can you give me an example? Uh, The general answer is no, as in you cannot just look at it and come up with an orthogonal basis. But I just want you to try so that you see that this is not a trivial task. Right? This is not easy to come up with, right? Has anyone come up with an orthogonal basis for this?
no.
Okay. So throughout what we have looked at since the beginning of this lecture is how angles and lengths can be used to produce something called an orthonormal basis, which evidently has advantages. That linear independence is obvious when there is orthonormality, and expressing any vector in that basis becomes very easy. But then now the question is, how do I even get it? How do I go from a usual basis to an orthogonal basis? Because going to orthogonal basis is enough, because here we have prescribed a way of going from orthogonal to orthonormal. So if I can start out with any basis, go to an orthogonal basis, that's enough. Because orthogonal to orthonormal, this part is already solved. This is done. So how to do this? We have said that these guys are important and these guys are very helpful. But now we will see how to manufacture this, or what is the obstruction to go from a basis to an orthogonal basis. Okay, so let's take a little bit of a break. Give me like 2 minutes. Around 9:12, we'll come back and resume. Okay, let's resume. So the objective now, sort of, is to find a way to make things orthogonal. So if I can start out with an arbitrary set and start making things orthogonal, then I'm in good shape. So this will be the roadmap for the next thing. This part of the road has been constructed, and we'll see how to go from basis to an orthogonal basis. So, as usual, let's start with an example. So I have, say, 1, 0, and let's say something like 2, 2. This is a basis. But is this orthogonal?
No.
It's not an orthogonal set. So the thing that is preventing this from being orthogonal is that the vector 2, 2, you could reverse the argument and do the same thing for vector 1, 0. The vector 2, 2 has a component in the direction of 1, 0. What does that mean? So I want to remove some part of 2, 2, which contributes some non-orthogonality onto 1, 0. Again, that is also not clear. I'm just trying to motivate certain things. If I look at 1, 0, and I want an orthogonal set, I'm looking at what space? I'm looking at this y-axis, right? I want some vector over here, some vector along this line. Now, can I write 2, 2 as a vector along that line and something else? That is what we will look at. And the obvious answer is look at this vector. So that is some, in some sense, the part of the vector 2, 2, which is orthogonal to 1, 0. And what is the part of the vector that lies along 1, 0? If you look at it this way, you have this guy.
Some scalar of 1, 0.
Some scalar of 1, 0, yes. In this case, we know the particular value also because it's quite
2,
obvious.
0.
That is 2, 0, yeah. So, and let me call this vector, this is v1, and let's call this vector v2. These red vectors, right? The ones that I've just drawn straight lines to. What is v1 plus v2?
So 2, 2.
2, 2. So it has to be 2, 2. Why? Because of the parallelogram. So I have just completed the parallelogram such that the sides are, the parallel to the given vector and an orthogonal vector. It's like it's always a rectangle. I can always make that rectangle. Is the point. So this v1 is orthogonal to v2. Sorry, orthogonal to 1, 0, and v2 is along 1, 0. Now, in this case, it was easy to see that v1 is equal to 2, 0, and v2 is equal to 0. Yes, I'm just taking the x component and the y component. But let us say I have now two vectors. Let's say 1 minus. So let's have this 1, 1, and then let's take 2, 1. The same thing I can do. I want to take only the component of 2, 1, which lies orthogonal to. So I can do the same thing where I draw an orthogonal vector and this orthogonal. Now, is it obvious what the components are?
Sir, for the previous one, you wrote V1 is orthogonal to 1, 0.
That should be 1, 0. So this is 0, 2. Right. This is 0, 2. This is 2, 0. Right? Yeah.
No, like before that line.
V1 is orthogonal to 1, 0. Yeah, that's correct. No?
Isn't V1? Okay, V1 is that one. Fine.
Yeah.
Sorry.
This is V2. V2 is the one which is along.
Yeah.
Yeah. So how do I compute what the value of this is? Can you guess what the value of that is? In the case 2, 1 and 1, 1, if I want to write 2, 1 as a sum of two vectors, one which is orthogonal to 1, 1 and one which is along 1. Can we deduce what that is? Any ideas? No? Does anyone want to say something? I think someone is unmuting themselves.
Sir, you can just say that it is some scalar of 1, 1.
Yeah, so that is an observation, right? It is some scalar. So let me call this guy as V2 and this guy as V1. So I want to express 2, 1 is equal to V1 plus V2 with the conditions that V1 is orthogonal to 1, 1 and V2 is along 1, right? So technically, you have only two variables. You can set up a system of equations and solve it. Let's do that as well. V1 is orthogonal to 1, 1. Anything that is orthogonal to 1, 1 in R2 is of the form x comma minus x for some x, correct? Because as soon as you have x comma y orthogonal to 1, 1, you'll have x plus y is equal to 0. So y is equal to minus x. So V1 has to be of the form x comma minus x. And V2 is along 1. So that has to be some alpha alpha, right?
Yes, sir.
Yes.
Now using this, can I deduce what that is? I want
I'm
2,
sorry.
1.
I'm sorry again. Why do we have to write x comma minus x?
So as soon as you have V1 is orthogonal to 1, 1,
Okay.
suppose V1 is xy, xy dot 1, 1 is 0. This is what I want, right? So this
Oh,
is
so
x
in
plus
that
y is
case,
equal
okay,
to
okay,
0.
okay, okay, okay.
So y is equal to minus x. So your point becomes x comma minus x. Is that fine? Should I write it down more clearly?
No problem, no problem.
Yeah. So this becomes x plus alpha minus x plus alpha. Now you can solve for x and alpha, right? Alpha is equal to half, I think, and x is minus half maybe. That 3 by 2. This is 3 by 2. And I think this should work. Right, so using all the machinery that we know, we did deduce what alpha and x are. In other words, the component of so V2, that is the component which is along the thing, that is given by 3 by 2, 3 by 2. And the orthogonal complement, orthogonal component is half minus half. But this is again simple cases. What about the most generic case? If I look at a vector and another vector in a vector space, how do I determine what is this guy? So once again, let me use red. So if I have something, if I drop a perpendicular, let's say, I have this guy to be V1, this guy to be V2. I'm only interested in V1 because, so let us not forget what our initial goal was. We were trying to go from a basis to an orthogonal basis. So if I have 1, 0 and 2, 2, if I take instead only this V2, sorry, the V1 guy, if I only take the orthogonal part, if I neglect the, sorry, not the V1, I want to neglect the part that lies along the initial vector. So if I do that, I can modify this to 1, 0 and 0, right? And this becomes an orthogonal basis. So instead of, so from V1, V2, let's not use V1, V2. So from 1, 0, 2, 2, I went to 1, 0, 2, 2 minus something. This something is the part which was along the first vector. So that is actually your V2. I removed something from the second vector so as to make it orthogonal to the first vector. And this can always be done is the claim. And how to do it in general, I'll be explaining now. And the linear dependence, you know that if I remove some vector from, so if I have a set W1 and W2, their span is the same as W1, W2 minus CW1. All of these things you know from the earlier things, right? So the span will be the same. Linear dependence will follow. A spanning set of size 2 will be a basis. So remember that this is what our goal is. So given a non-orthogonal set, I want to modify the vectors in it such that it becomes an orthogonal set. And I'm achieving it by looking at what is the component of the second vector in the direction of the first vector, and then subtracting it to get an orthogonal vector. So in general, if I have two vectors, V and W, again, you have, if you drop a perpendicular to it, think of all of these things in the usual sense, in R2 with the standard dot product, if you will. So you have a V1, V2. So if I can write V as V1 plus V2, and I know V2 lies along W. And instead of the basis or linearly independent set VW, I'll consider V or W and V minus V2. And V2 is nothing but C times W. So these two will be two linearly independent sets which span the same basis. So, span the same set. They have the same span. So changing from this to this, what has happened is your basis, the random basis that you started out with, has now turned to a orthogonal basis. And then you can make it into an orthonormalization by just dividing it by the norm, which is called normalization. But how do I find the component V2? Like, what is this C? The C is still not known, right? I'm just saying that this can be done, but how do I actually go about doing it? So consider this angle. This is angle theta. Now, what is cos theta?
E dot T.
V2 by V.
It's not V2 by V. So let's evaluate
Actually,
cos theta
sorry.
two ways.
Length of
It
V2
is,
by.
yeah, norm of V2 by norm of V. Correct?
Yes.
Why is this? This is because this is a right triangle, this is an adjacent side, and this is the hypotenuse. And this is the usual definition of cosine of an angle. Once again, reminder that all of this is being done in R2 with your usual coordinate geometry. On the other hand, we also have cos theta given by the inner product. Like what is, according to the inner product, what is cos theta? Theta is the angle between V and W, right? So what is cos theta?
Dot product of P and W divided by
Divided by,
Norm
square
of
root
V times
of
norm of W.
W. Yes.
right? So if I forget about this guy and equate these two things, the norm of V2, this is something that we don't know. This is V dot W divided by norm of W Am I missing a W somewhere? No, this is fine. This is okay. Now I've actually found out what norm of V2 is, correct? But V2 by definition is C times W because it is the component which lies along W. So what is norm of V2? This is mod C. I'll just take C, but you'll have to be a little careful when it is on the other side and all that. So this C will be equal to V dot W by W square. I've used that norm of V2 is V dot W by W over here. I've substituted that for this and then brought the W norm of W down and I've got this thing, right? So finally you have V2 is V dot W divided by norm of W square times W. So this is a scalar times W. Is that fine?
Yes.
So this was the general vector in R2, but it's still the general vector V and W. We did not appeal to 2, 1, 1, 1, all of these things. Here we found out the solution. So let us just verify that that is correct. The formula that we got was V dot W divided by W square times W. That is your V2. In this case, my W is 1, 1 and V is 2, 1. So let's do 2, 1 dot 1, 1 divided by norm of 1, 1 square. What does this turn out to be? 2 plus 1 is 3. Norm of 1, 1 square is 2. 1, 1. So this agrees with this, right? It is 3 by 2, 3 by 2. And what is the other component? It is 2, 1 minus V2, which is half minus half, which is exactly this component. So this vector, let me highlight this. This vector seems to be what captures the projection of the vector V onto W. So this is what is called projection of V onto W. If you look at this, and one very natural way to look at it is, what is the, suppose there's light from above, what is the shadow that V casts along the line of W? So you're assuming that the light is coming from a perpendicular direction to W. Then the length of the shadow, or the shadow that it casts, is called the projection. Now, if V is orthogonal to, okay, let me take that separately. So this is to be thought of as the component of V along W. All right. A quick check with all of these. Now this was in R2 and usual inner product, but the same thing is the definition of projection in a general vector space. The projection of a vector V onto a vector W is denoted by projection V onto W and is given by V dot W divided by norm of W square times W. So this is the formula for, this is the formula, and this is something that you have to remember. But note that it is motivated by very natural considerations and with the goal that we want to remove projection. So by removing the projections from the given vectors, what we'll be left with is an orthogonal part. And that is our recipe to manufacture orthogonal or orthonormal basis. That will be given in more detail. But here let's do a basic check. If V is orthogonal to W in the first place, what is projection of V onto W? So of course you could appeal to the formula, but I want you to tell me what it is without looking at the formula. So if I have a vector V and W, this is how you should always think about it. What is the shadow?
Is it 0?
What is, yeah, it has to be 0, because if something is upright, then it does not cast any shadow. It's like if the sun is above your head, you'll have a 0 shadow. So that is how you have to interpret it. But then if you look at the formula, you have a V dot W component along for the projection. And if my V and W are orthogonal to each other, of course, V dot W is 0 and you'll get the 0 vector itself. And that is to be expected. So this is 0. And yeah, the main point to note is that this is something that is expected. And ideally, I want orthogonal vectors, which means they have zero projection on one another. Another way of defining an orthogonal set would be to say that they have zero projection on each other. So now another check, which is natural, is what is given any v comma w. Now I'm not assuming that they're orthogonal to begin with. What is the projection of v minus projection of vw onto w? So what am I doing? I'm taking two vectors v and w. I'm looking at projection of v onto w. I'm removing it from v and then again projecting it onto w. What would I
Sir,
expect the projection to be?
So can you show it geometrically? I don't follow.
Yeah.
sir,
So if I
0.
have, yeah, it has to be 0. So if you look at v, you look at w. If I look at the projection, right? This is projection vw, and I do v minus projection vw. What is that vector? V minus projection vw.
That horizontal thing.
Yeah, by triangle law, this would just be, I don't know where it starts. I think it's over here only. It's like this. But this is what we were doing over here, right? I was writing V as a projection component plus an orthogonal component. So what I'm trying to stress or suggest is that once I remove the projection part out from a vector, what you are left with is an orthogonal vector. Correct? So this V1, which is what is left after I remove V2 from V, that should be orthogonal. And what is the projection of a vector which is orthogonal onto a vector that is 0? So this has to be 0. Geometrically, if I look at V and W, if I remove the projection, what I'm left with is this. So this brings us to the back to the goal, as in how do I get orthogonal basis from a normal basis? I just remove the projection. I just remove the corresponding projections. So let's do that example. What was the example? I think it was x plus 3y minus z is equal to 0. And the basis that was manufactured was 101. You could do this with any basis. I think it was 013. Is this what we had come up with?
Yes.
Yeah, 101, 013. Now I'm not going to draw 101 and 013 in the 3D plane or in the 3D space. But let's look at 101, we'll keep it as it is. I want to modify 013 and remove the projection of 013 onto this. So what is projection of 013 onto 101? Note that these are some vectors in space which do look like this. As soon as you have two vectors in their two-dimensional space, they actually look like this. So without drawing out the diagram, I can compute this to be 013 dot 101 divided by the norm of 101 square times 101. Right? This is just v dot w divided by norm of w square times w. This is a formula that you need to remember. This is probably the only formula that you need to remember when it comes to projection. And when you do things like Gram-Schmidt orthonormalization, it's a little bit more involved. But that's okay. So when we get there, you'll see what I mean. And if you compute this, this is a 3 divided by a 2, 101. So if I look at this vector 0, 1, 3, by itself, we have checked that this is not orthogonal to 101. And the component of 0, 1, 3, which is in the direction of 101, by which I mean, suppose this is 101 and this is some 0, 1, 3, this vector, this vector is actually 3 by 2, 0, 3 by 2. So if I remove that, what I'll be left with is the vector that I want. So that's what we are going to do now. So if I look at 0, 1, 3, all this guy u2, 0, 1, 3 minus 3 by 2, 0, 3 by 2. What is the answer? 1, 3 by 2, right? Now, two things to check. Does this lie in my given set? Does this lie in the plane x plus 3y minus z is equal to 0? It has to, but let's verify that it actually does belong there. Does it?
Yes.
This is 0. So we are good. So this vector still lies in the given plane. Is this orthogonal to 101? That is also easily verified to be 0, right?
Yes, sir.
Yeah. So 101 minus 3 by 2, 1, 3 by 2 is an orthogonal basis. Yeah, basis in this case. Orthogonal basis for the given space. Even though initially it was not obvious whether it had an orthogonal basis or how to construct an orthogonal basis, I suppose now you guys are convinced that there is a way to manufacture one.
So we have to
Right?
actually take the V minus projection of V
Yes.
onto U as the second element in the basis of the
Yes.
or second element of the orthogonal basis, right?
Yes. That's what I've been saying over here, that check this guy is orthogonal. V minus projection V is orthogonal to W. That's why it gives a projection of 0. So if you have V comma W, then V comma, okay, I've been using projection of V onto W. So let's say W comma V. If I start out with this set, what I want is W times V minus projection of V. So projection is the whole part which lies along, and whatever remains is something that lies orthogonal. That's the that's like the punchline of all of this. And at least for a set of two vectors, now I hope you know how to do basis to orthogonal basis. And if you normalize this, you'll get an orthonormal basis also. Is that fine?
Yes.
Or should we do one more example? Do we need to do one more example, or shall I go ahead?
Yes, understood, sir.
Okay. The next thing that we'll be looking at is now projection onto a vector we have done. what we'll do is, in the next step, is projection onto a subspace. So here we had only one vector and projecting it onto another vector. Right. So there's one more interpretation of this, which maybe I'll take in the next session also. That another way to look at the projection is look at this entire line. If I have V and W, if I project V onto W, this is the projection. So projection is the point or is the vector on the line that you're projecting it to, which is closest to V. If you take any other point, this distance will be more than this, right? So that is another interpretation. I'll probably take it up in more detail in the next session, in the Sunday session. So now you know how to take projection of a vector onto another, motivated by this diagram, this theta, and so on. But what if I say have a plane and I have a vector which is pointing outward from the plane, and I want to look at the projection of this vector onto this. Once again, intuitively, it makes sense to drop the perpendicular and call this vector as the projection. But now how do I compute that vector? That's the question. Right? And this is just a two-dimensional plane. What about more like higher dimensional subspaces? Is there a notion of projection of a vector onto a subspace? So here also, even though we said projecting a vector onto another vector, we were essentially projecting this vector onto the one-dimensional space spanned by the vector W. So here we did a particular case of projecting a vector onto a subspace of dimension 1. Now we are going for higher dimensional subspace. So here let's look at what it means when we say projection of a vector onto a subspace. We have 10 minutes. Let's quickly cover it. This is not much of a jump to give a proof that agrees with your geometric intuition. That time might not be sufficient, but I'll just say it now, and maybe if required in the Sunday session, I'll deal with it in more detail. Now, suppose I have a subspace W. This has a basis, has an orthonormal basis. Orthogonal is also sufficient, but I think orthonormal is considered as the convention is to take an orthonormal basis. Let me call this W1 up to WK. Suppose it's a k-dimensional subspace. So this is some sort of an argument by induction. So do you guys know what it means to say argument by induction?
No, sir.
Okay, then let's avoid that terminology. So suppose this is just a k-dimensional subspace. Projection of V onto the subspace W is nothing but summation of projection of V onto WI. So if I have a plane and I want to project some vector onto this plane, what I do is I take an orthonormal basis. I look at what this vector projects onto this line and what this vector, see, this gets messy and probably not very revealing geometrically. But the idea is that an orthonormal basis gives, in some sense, the measure of all directions and in the most independent way possible. So you look at projections along each component and you add all those vectors up. all of this will, of course, be a vector in W. The projection of a vector onto a vector is a vector in the direction of W. So projection of V onto W is a vector in the direction of W, right? So this each of these vectors will be a projection, will be a vector in the direction of Wi, and each of the Wi are uh, vectors in W. So the whole vector is in W. So this projection of V onto W is a vector in W, which is defined like this. And how do I
Do
compute
they
it?
get added up?
Yes, they get added up.
Or
So
they
let's,
exist as a list? I was thinking that they exist as a list. Like for basis 1, it has a projection this. For basis 2, it has.
No, summation is there. Summation is there, na?
yes, there should be a summation. I'll tell you why. So let's take an explicit example to see this clearly. Let me take the vector 1 comma 1 comma 1, and I want to project it onto the xy plane. What would you think the answer should be? So what is projection along the z direction, so to speak? Projection onto the xy plane. So suppose there's light shining from
110.
above.
It's 110.
Yeah.
110.
So this is what you would expect it to be, right? So let us, my W is the xy plane. Ah. So which has a basis, which has an ordered, orthonormal basis 1001, 100, 010. This is an orthonormal basis for W. Now, what is projection of 111 in the direction of 110? This is 111.11100 divided by norm of 100, the square times 100. And this denominator is just 1. So what we are left with is, and the numerator, there is just 1. So this is just 10. Similarly, you can check that projection of 111 onto 010 is just 010. And so these are two vectors, which are projection onto an orthonormal basis of the given subspace. Right? And then you have to add them. So you cannot just list them, because the projection of a vector onto a subspace in turn has to be a vector. And if you have two vectors, you add them, you get another vector. Right? So projection of 111 onto W, let's call this guy an example. This is a very trivial example. You can mess around with more difficult examples. This thing is 110, which is 100 plus 010. So you have to take individual projections. So okay, let's just write that down clearly. Given a subspace, W, with an orthonormal, I'll just write ON, orthonormal basis. Orthogonal is, once again, I'm just saying that orthogonal is enough for this method, but let's keep it orthonormal because computations will be easier. Compute projection of V onto Wi for each I, and then add. So this is how you compute the projection of the vector onto a subspace.
Sir, in our example, where did we add them?
This and this we added. Let me call it 100 plus 010 This is equal to 110. So here I'm saying that this is geometrically, it seems like this is the right answer, but let us see if this formula does give me the same answer. So I computed projection on the first vector, which is 1, 0, 0. I computed the projection onto the second vector, which is 0, 1, 0. And then I add them up, it is 1, 1, 0, which agrees with what I believe to be true, and which is correct. Is that clear?
Yeah. So it's indirectly we're scaling the basis of that plane
Yes, you're
in some sense
not
to
scaling
get.
the basis. You're looking at the components of the given vector along this basis.
Yeah.
You're looking at individual. You could have taken any other orthonormal basis for W as well, and you would end up with the same answer because it is independent of the basis chosen. So let's maybe do that as well. So the same XZ plane, I can take 1 by root 2, sorry, XY plane, no? XY plane is what we would do. 1 by root 2, 1 by root 2, 0, and 1 by root 2 minus 1 by root 2, 0. This is also an orthonormal basis for this. Now, what is projection of 1, 1, 1 onto 1 by root 2, 1 by root 2, 0? So this you can check to be square root of 2 times 1 by root 2, 1 by root 2, 0, which is 1, 1, 0. Do I want 1, 1, 0? Let's see. The projection of 1, 1, 1 to 1 by root 2 minus 1 by root 2, 0. This again you can check to be actually 0. 0 meaning 0, 0, 0. Once again, if you look at the sum of these two things, it is 1, 1, 0.
Yeah, I think I get it. We are actually creating a linear combination of the bases so that the
Yes,
reflection. Yeah,
and this basis is chosen to be an orthogonal basis because then it is, in fact, orthogonality is required. So what you're looking at is you're just looking at this projection and expressing it as a linear combination of the W1. And expressing something as a linear combination of a given basis is easy when it is orthogonal or orthonormal. So you start out with a basis, orthonormal basis for the given subspace, and then measure components in each direction and add them.
so it feels like even if the basis is not orthonormal, it should work, right?
Orthogonal, it will work.
No. Sorry, no. Even if it's not orthogonal, it should.
If it is not orthogonal, uh,
It's just intuitive. I mean, this is all
yes,
new
yes,
to me.
yes, I get it. I get it. I get it. Uh, I think it will still work. Yes. With any basis, it should work. Wait a
Maybe
minute.
the formula breaks. I don't know. The projection breaks.
No. Just give
Yeah,
me a moment. Let me
so
think
I
about it.
think that henceforth we could find the projection of any vector onto any plane, whether or not it is orthogonal or not, using this formula.
You can do it for any. Okay. Right now, I'm kind of blanking. I'll think about it and I'll tell you on Sunday. On the face of it, it seems like it should work for any basis, but will it give this formula or some variation of it? I don't know. For orthonormal, it definitely works. For orthogonal also, it definitely works. This much I know. And I think in the props videos, it is said orthonormal. You start out with an orthonormal basis. So let's keep it that way itself. And then, yeah, I'll clarify this in the next session.
Okay, no problem.
So yeah, that's about projection, but we have sort of not addressed the core issue that how do we even get this in the first place? How do I even get an orthonormal basis? So that is what we will do in the next session. As in, we have partially answered this in the case of two vectors. We just remove the projection of one vector from the other, and then what you get is an orthogonal basis. Normalize it, you get an orthonormal basis. But what if there are three vectors, four vectors? This is not immediately clear how to proceed. But there is a very standard algorithm to do the most general case. Start out with any basis and transform it into an orthogonal basis. That is called the Gram-Schmidt orthogonalization. Gram-Schmidt orthogonalization and orthogonal transformations. And yeah, there's one more topic, I think, projections as linear operators. These three topics I'll be covering in the Sunday session. So that's
And
it
the
from my side.
rotations, do we have rotations in this way?
Yes, it is in the same week. Yeah, I'll be covering the rotations as well. Orthogonal transformations, rotations are part of orthogonal transformations. So I'll be covering that as well. Week 9 must be multivariable calculus. No? Is it? Does anyone
I'm
know?
not sure, but I know that
Yes, sir.
linear combination. Linear algebra ends in week 8.
Yeah. Then it is multivariable calculus that is week 9. So this will be, I won't say the end of linear algebra, but yeah, this will be the conclusion as far as this course goes. It will come up in multivariable calculus as well. But yeah, there's one more session. So in that we'll wrap up. So yeah, that's it from my side. Any
Slightly
doubts?
we are moving towards geometry.
Yeah, you could say that. Yeah. So this is what happens at, like, linear algebra is what happens at the tangent level or infinitesimal level, and the more global picture is multivariable calculus. That won't probably make sense to you right now, but yeah, I'll once you see the topics in multivariable calculus, things will make sense.
Also, sir, about this removing the projection from V. Do you remember that
Yes.
step? I think I understand that, but it's a bit unintuitive to just remove a vector from a vector.
Vector minus a vector is there, right? It's just vector subtraction. You're
Yeah.
subtracting the projection
Algebra
vector.
is okay, but
Yeah. So okay, if you want to see why that is true, as in okay, let me just write this out. V minus projection V, the inner product of this with W. What is this? This is VW minus projection of V W with W, right? So that is VW W divided by norm W square with W, which is VW minus this whole constant comes out, and what you're left with is WW, right? Are you following the symbols?
yes, yeah.
So this is one, this get cancelled, and this minus this is 0. So this is the vector which, when you remove from the given vector, leaves me with an orthogonal vector, which is intuitively also okay, and by the formula also this is very clear.
Okay, yeah.
Sir, while you were explaining the geometrical meaning of V minus projection of W on V, I didn't get that. Can you please
V on
explain it
W.
again? V and W, sorry.
Yeah. So our goal at this point was to start out with, well, here the order is kind of funky, but that's okay. So WV is a given set, linearly independent set. I want to manufacture a orthogonal set, which is automatically linear independent. I want something more than linear independence. I want orthogonality. So what do I do is I construct the rectangle that V is a part of. So given any vector, take, for example, just in a coordinate plane, you can make sense of what a rectangle is, right? The rectangle defined by this vector. But the
Yes.
axes are somewhat, like chosen by us. We say that this is the axis, but given any vector, I can make a rectangle using this vector with this as one of the sides, as in the direction data defined by the other vector. This W might be something else. This need not be one of the coordinate axes. You can form a rectangle in such a way that
The vector is the
one
diagonal.
of the given vector is a diagonal, and the second vector that you are looking at is one of the sides of the rectangle. So if you look at that rectangle, the side that lies along the other vector is actually the projection, and the side which is not that one, that is the orthogonal complement, as in the orthogonal component. So by law of vector addition, you have that this plus this is this, right? So V is this projection vector plus this orthogonal vector.
Yes, so V equals to V1 plus V2.
Yeah, so if I have V is equal to V1 plus V2, and I'm calling this V2 as the projection, V minus projection will be an orthogonal vector to the given W. So what is the role of W over here? It just gives me the direction along which I want to draw my rectangle on. Of course, all of this is just to support your visual intuition. The actual math is given in symbols over here. If
Okay,
you
sir,
don't
get
even
it.
if you don't get the geometric intuition also, this is good enough to work with it. But it's always nicer to have this sort of diagram in the back of your head.
Yes, sir. Thank you.
Did I answer your question?
Yes, sir. Yes, sir.
Yeah.
Also, sir, with if we have a basis and we
Yeah.
were to make it orthogonal,
Yes.
so the steps that you showed works. But I was thinking, if I take one of those vectors of the basis and I find the perpendicular vector to that vector. I mean, we'll have an infinite vector, but I just want the form of the perpendicular vector.
Just a moment. Let's take an explicit example maybe. So let's say I have x plus y plus 2z plus 3w is equal to 0. This is in R4. Okay. This is my w. So one vector would be maybe 1 minus 1, 3 minus 2. Okay, this is one vector. I know this is a three-dimensional space. I can come up with more vectors, but okay, let's see. If I take 0, 0, 3 minus 2, this will also be a vector that is also there. And what else can I do? I'm not doing it very well, but maybe things like 1 or 3, 0, 0 minus 1. Maybe this is not, maybe this is a basis. Okay, let's say we have this basis. If this is a linear combination of these two, then yeah, we'd have to do something else. But no, this cannot be a linear combination of that. Yeah, this is a basis. Okay, fine. So let's try to do what you are proposing. What were you saying?
Yeah, I think this example already tells me that it won't work.
Okay,
I
but
what
let's just suggest whatever you were going to
So I
suggest.
was
Let's
saying,
see.
just take one of the vectors. Let's take the first one, and let's.
Okay.
I don't know how to, but let's find the vectors that are perpendicular to this vector. Like
Yes, you
there'll be
will
infinite ones.
soon. Yeah, there will be infinite ones because so in this case that was easier because we had a two-dimensional space.
Yeah, that's what
There,
I realized.
yeah. So if you have a two-dimensional space and you have one vector, there's only one direction which is orthogonal to it, right? So
Yeah.
it will be, everything will be c times some vector. But if you have a three-dimensional space and if you have one vector, the orthogonal complement of that is a whole plane.
Yeah, yeah.
So that becomes very complicated very quickly.
Yes, I see that now.
Yeah.
Okay, thank you, sir.
Yeah, no problem. Yeah, if there are no more doubts, let's wrap up. And if you don't have any doubts, feel free to leave. I'll stop the streaming as well.